Good morning, good afternoon, and good evening to everyone. And thank you for giving me this opportunity to say something about the current status of the uranium and plutonium isotope ratio measurements done by mass spectrometry at PTB. So my name is Janine Eberhardt, and I started working at PTB back in 2012 in the working group in organic analysis led by Olaf Rienitz. And this working group does have a couple of different kinds of mass spectrometers. And therefore I used already a different set of them. And yeah, I used to measure the isotope ratio composition or the isotope ratios for the determination of mass fraction in different kinds of samples. So back in 2016, I switched to the working group environmental radioactivity. And this working group and also the department radioactivity didn't have any mass spectrometers so far, but they've decided to change this. And so in 2019, we've bought this mass spectrometer. It's a multi-collector, inductively coupled plasma mass spectrometer. It's Neptune Plus by the company Thermo. And so we've got a couple of reasons actually why we bought exactly this instrument, and I want to give you some notes about our motivation for this mass spectrometer. The future goal for our working group will be the certification of environmental reference materials for their absolute isotope composition and activity concentration. And yeah, we've discussed this already a little bit today, but especially a little bit more in the video tutorials that are online, that there's not always an isotope reference material available. And therefore, sometimes it's necessary to prepare gravimetric isotope mixtures. And these solutions can have a large variety of isotope ratios. They can have 5 orders of magnitude difference. And if you want to measure these solutions, then it's necessary that the correction factor, the calibration factor, is independent of the isotope ratio. And this is only given if you're using magnetic sector field mass spectrometers. And and so another reason was, of course, the smallest measurement uncertainty is achievable with this kind of instrument. And also we can simultaneously and separately detect the plutonium isotopes 239 and 240. Yeah, and with this I come to the practical part of my talk. I will start with the uranium measurements. One of the first samples we had in the lab was an uranium activity standard from another working group. And the goal was the determination of the isotope composition. And as I mentioned before already, when you're measuring something on a mass spectrometer, there's always a mass bias occurring, meaning that every measurement results in intensity ratios and not in the isotope ratios that we are actually interested in. And therefore, it's always necessary to perform a calibration for the measurement. And for this, it was, let's say, relatively easy. We bought an uranium isotope reference material, the IMM 184. And then we applied the equation, which you see on the bottom of the slide. For the example of the 235 uranium to 238 uranium of the sample, I used this equation on the bottom. And now I want to show you the uranium detector configuration. Just give you a sign that I measured all the uranium, the naturally occurring uranium isotopes, 234, 235, and 238 uranium in just one single measurement. And during this measurement campaign, I reached detection limits. I know we've talked about this already, but I can also say something about how I calculate this at the end. The detection limit I reached were around 28 picograms per gram for the uranium isotopes in terms of mass. And in terms of activity, I reached around 6 millibecquerels per gram for the 234 uranium and 2 microbecquerels per gram for the 235 uranium and around 300 nanobecquerels per gram for 238 uranium. Yeah, and with this, I come already to the results of the uranium measurement. You see now on the y-axis the different, or the uranium isotope ratio of 234 to 238 uranium, and on the x-axis the different measurement days. Yeah, and for this campaign, I reached a relative expanded uncertainty of 0.065% with K equals 2. And for the other uranium isotope ratio of interest, the 235 uranium to 238 uranium, I reached a relative expanded uncertainty, even a factor of 2 lower, of around 0.031%. Excuse me. And yeah, so with this, I already come to the plutonium measurements, which were done at PTB already by mass spectrometry. For this, I had as a sample an unirradiated mixed oxide fuel, and the goal was again for the determination of the plutonium isotopes. But the situation with plutonium is a little bit more, complicated, you could say. A little bit more difficult because one reason is that we don't have plutonium isotope reference material, and therefore I used the uranium isotope reference material as to calculate the correction factor for the measurement. And the second reason why it's a little bit more complicated, we are measuring the plutonium isotopes on a different detector compared to the uranium isotopes. And therefore I need to do a so-called cross-calibration. And this resulted in that I also need to measure the uranium isotopes 233 and 236 uranium. And to give you a better picture of the detector configuration, you can see now this table on the slide. And maybe you remember that the detector configuration for uranium, for just measuring uranium, was a little bit more, less crowded, I would say. And so you see now on the first row for T1, we're measuring all the plutonium isotopes at one measurement, and the next 3 measurements from T2 to T4 relates to the cross calibration actually only. And only the last slide, as the last row, T5, refers to the measurement of the uranium isotopes, which is needed for the calculation of the calibration factor. Yeah, and let's have a look at the calculation of the calibration factor. In this case, I need to apply the so-called exponential law, and I'm using the uranium standard as for the calibration. And therefore, I also need to include the molar masses, which you can see on this in this equation. But this is a general equation, and now you can see the detailed equation for the plutonium measurement. In this case, as an example, the 240 plutonium to 239 plutonium. Yeah, and based on this equation, we can see now the results for plutonium. On this plot, you see now on the y-axis the 240 plutonium to 239 plutonium, and on the x-axis the different measurement days. And you can see now that for 240 to 239 plutonium, we've reached a relative expanded uncertainty of around 0.8% with K equals 2 again. And for the other plutonium isotopes, 241 to 239 plutonium, we reached a relative expanded uncertainty of around 0.91%. And for the last isotope ratio of interest of plutonium, it was 242 to 239 plutonium. We reached a relative expanded uncertainty of 0.97%. And now I want to summarize the plutonium measurements. Therefore, you see in this table, in the first column, the different plutonium isotopes. And in the second column, you see now the relative expanded uncertainty, which I showed you already. And now again, the detection limits. First, they were calculated in terms of mass and then in terms of activity. So in terms of mass, we have around 30 femtograms per gram for each plutonium isotope. And we have around 66 microbecquerels per gram for 239 plutonium, around 244 microbecquerels per gram for 240 plutonium, around 107 millibecquerels per gram for 241 plutonium and around 4 microbecquerels per gram for 242 plutonium. Yeah, and with this, I already come to the next activities which are planned. And the first thing was already mentioned by Michael Winchester. There is this key comparison, CCQM K178, which is organized within the Inorganic Analysis Working Group. And the goal is the determination of the uranium mass fraction in a soil sample. And the samples are planned to be shipped in February, so this month actually. And so the results should be sent to the organizer until the end of September. And we are planning to apply the double isotope dilution mass spectrometry technique to reach the lowest measurement uncertainties. Yeah, and so the other activity has already started last year in October. It's a European funded project, Metropoem. It will last for 3 years, and the title is Metrology for the Harmonization of Measurement of Environmental Pollutants in Europe. But I won't go into more detail about this European funded project because Dirk Arnold will say a lot more about this project tomorrow during his presentation. So to summarize my talk, first of all, I started with some motivation points for us why we got multi-collector ICP-MS at the Environmental Radioactivity Working Group at PTB. And then I showed you the difference between the measurements for uranium and plutonium done by mass spectrometry, and of course some insights in our next activities. Yeah, and with that, I want to thank you for your attention.